Hello friends, welcome back to C Field Academy, where we learn together from each other. So this is another video related to the deadlock in operating system, and we are going to discuss today the resource allocation graph algorithm, which is used for deadlock avoidance. So first things first, this algorithm is not discussed in detail in any of the books, so I have tried to come up with the examples and the details as clearly as possible so that the concept can be made clear. So these are the topics which we will discuss today. We'll just briefly touch upon what deadlock is and the deadlock avoidance technique for avoiding deadlock. In fact, we have another video on our channel that is specifically dedicated to deadlock, and wherein we discuss deadlock in much detail. I would recommend you to go through that video, and in fact then it would pretty much make sense where the resource allocation algorithm fits in the entire context of deadlock. So then we will start with the resource allocation graph algorithm. We will try to define it, discuss various aspects of it. We will see under which conditions we can apply the algorithm. Then we will go ahead and discuss the algorithm, as in the pseudocode, the steps of the algorithm. We will then move on to a detailed example, in fact in very greater detail, step by step, the execution of the algorithm and how to use it to detect whether the system is in a safe state or an unsafe state. Finally, before we end, we will have an exercise for you guys, which you can apply the algorithm on. So cool, let's get started. So first, a little bit about deadlock. So deadlock is a situation wherein there are set of processes, there are set of resources, and the processes are blocked because they are holding certain resources and they are waiting for some additional resources to be allocated, and those additional resources to be allocated are held by some other process. So in summary, none of the process are able to proceed, or they are stuck waiting for the resources when they will be available. So this situation is called a deadlock. So deadlock avoidance is a technique which we use to handle deadlocks. So even before deadlock occurs, we maintain a state of the system, whether the system is safe or unsafe, and we then ensure that the system doesn't go into the unsafe state. And in fact, if the system doesn't go into an unsafe state, there is no chance of deadlock. So here is how it looks, from the concept of context of safe and unsafe state. So we have a safe state which looks like this, and we have an unsafe state. And in fact, when we are in unsafe state, it's still possible that deadlock hasn't happened, but deadlock avoidance technique is used to make sure we are always in the safe state, even though there is an overhead in terms of detecting deadlock or computing the graphs and stuff like that. So let's go ahead and start a little bit first on what a resource allocation graph is. So a resource allocation graph is a graph where we represent the processes by circles. We can see here processes P1, P2, P3, three processes are represented by circles, and resources are represented by rectangles. And in fact, when there are multiple instances of each resources, we denote them using dots, like we have here for R2. So there are two instances of R2, I've labeled them as 1 and 2. And similarly there are 3 instances of R4. Then we have some edges. So first, request edge. So request edge is an edge from the process to the resource, which means the process is asking for that resource to get allocated so that it can proceed. So in this graph we see that process P1 is requesting R1, so there is a request edge from P1 to R1, there is a request edge from P2 to R3, there is a request edge from P3 to R2. So this is a request edge. Then assignment edge. So assignment edge is a directed edge from the resource to the process, indicating that the resource is already held by that process. So here we see that resource R2 is already allocated to P1, so we have an edge here. Resource R1 is allocated by P2, allocated to P2, and R3 is held by P3. So that's why we have edge from R3 to P3. Now similarly there is another concept called as a claim edge. Now this edge comes in the context of time, wherein there are certain requests that the process has in future. So these are similar to request edges, but they are represented in a dotted manner, indicating that the request is not current, but the process will request that edge in future. So here is an example. P2 will request an instance of R4 in future. That's why we have a dotted edge from P2 to R4, and there is also a dotted edge from P3 to R4, indicating that P3 will ask for an instance of R4 in future, but this is not the current request. That's the difference between the claim edge and the request edge. So using a resource allocation graph we can detect deadlocks. So let's see what we can do using a resource allocation graph. So whenever there are no cycles in the graph, which means deadlock does not exist. That's an important thing to know. Now here these are directed graphs, and hence cycles would mean directed cycles. So if we have no cycles in the resource allocation graph, then we are sure there is no deadlock. If there is a cycle and resources are single instance, then deadlock exists. But if there is a cycle in multiple instance type resources, we still are not sure whether a deadlock exists or not. Now here is an example. The first example shows that there is a deadlock, and let's see why there is a deadlock. If you notice, P1 is allocated with R2 and P1 is requesting R1. Then R1 is held by P2 and P2 is requesting for R3. R3 is held by P3 and P3 is requesting R2, and in fact R2 it's also held by P2. So if you notice, there is a circular wait here and there is a cycle, and in fact there is a deadlock as well, because none of the processes can proceed. Each of them are waiting for some resources to be allocated, which is held by other processes. Now in the other example where we see there is no deadlock, even though there exists a cycle, now there may seem that there is a cycle here from P1, R1, P3, R3, but deadlock does not exist. Why? Because R1 is multi-instance, and once P2 is finished with R1, R1 will be free, and then P1 can proceed with R1, and once P1 can proceed with R1 and P1 releases R2, R2 can also be allocated to P3 and all the processes can then proceed. So even though there is a cycle, there is no deadlock here. Cool. So let's go ahead with the algorithm definition and the conditions that are needed, when we can apply this algorithm. So resource allocation graph algorithm is an allocation and deadlock avoidance algorithm. So which means it tries to avoid deadlock by ensuring the system is in a safe state. And how does it do it? It avoids the fourth condition, which was the circular weight condition, which was a necessary condition for a deadlock, by ensuring the system is in a safe state. So if circular weight condition is confusing, I would request you to go back and look at the previous video on deadlock. That would make it pretty clear. So when can we apply this algorithm? So we cannot just apply the algorithm in all conditions. There are certain conditions when we can apply this algorithm. The first, resources must be of single instance type, which means if there are multiple instances of the resource, we cannot apply the algorithm. Processes must declare the need of the resources well in advance, even when they come, or when they start executing, they have to declare the resources to the system. Thirdly, processes must return the resources in a finite amount of time, so that it can be allocated to other resources, and then the system can continue. Lastly, resources do not deplete, which means resources can be used over and over again without getting without wear and tear. So yeah, cool. So these are the 4 conditions where we can apply the resource allocation algorithm. In fact, the conditions are pretty similar to the banker's algorithm, which we use for deadlock avoidance as well. So let's go back and see the pseudocode of the algorithm, which means the steps of the algorithm. Now the steps might be a little involved, but don't worry, we will go through it with a detailed example, so that things will be pretty clear. So the first step of the algorithm, as we first step of the algorithm is to create a resource allocation graph, which we just saw in the previous slide, with the current set of allocations. Now step 2 is to add claim edges to the processes in the resource allocation graph based on the future requests. Now step 3, which is a little complex because it involves looping through each of the processes and each of the requests of the processes. So step 3 is to first find a process which has future requests, and then for each of its requests we first see if that request is possible, which means we first convert its claim edge to an assignment edge in the graph. Then we will see if there is a cycle in the graph. We have to make sure there are no cycles. If there is a cycle in the graph, we cannot perform the allocation, which means we actually go back and again change the assignment edge to a claim edge, indicating that this resource cannot be allocated at this point, but maybe at some point in future. But otherwise, if there is no cycle, we will keep the allocation, which means we'll keep the assignment edge, and then we will move ahead to its next request of the process. And we then, once we are finished with the requests of the current process, we'll go back and then we will repeat the same step with other processes, and we keep doing it till all the processes we are done with we are done with the other two or the other processes as well. So which means we have to cover each and every request for each and every process. Once we are done adding the assignment edges, now we will go through the graph and then see if we can simulate a process to its completion, which means we can let some process execute and then basically we have to see if need of the processes is complete, and then we will let the process execute, and then we will remove that process from the graph and we will free its resources. So once the resources are free, because resources are free, now some more requests can be allocated, or some more resource requests can be allocated. We go back to step 3 and repeat the whole process again, the process of going through each request from the resource. We keep doing this from step 3 to step 4 till we are done with all the processes, or somewhere we are stuck where we cannot proceed further, in which we come to step 5, which is the last step. Now at step 5 we will check if our resource allocation graph is empty, which means all processes have been completed successfully, or we were able to simulate all processes to get completed successfully. Then we are in safe state, which means we are good. There is no deadlock, or there is no chance of deadlock in the allocations which we have. Otherwise, if we are stuck somewhere and we were not able to proceed, or we were not able to simulate all the processes, we are in an unsafe state. So similar to the banker's algorithm, I would say. So cool, all these steps were a little involved, but let's get to an example to see how we can apply these algorithms and to see how this algorithm works. Cool, so here is an example. So in this question we are given a system where there are 3 processes, P1, P2 and P3, and there are 4 resources, A, B, C and D. And remember, since we are in the resource allocation graph, there will be only single instance of each of the resources, because we cannot apply the algorithm to multi-instance algorithms. So there is a max matrix, or the maximum need of each processes is over here, which means process P1 needs A, B, C and D for its execution, all the 4. Process P2 needs A, B, C for its execution. P3 needs C and D for its execution over its lifetime, not at this moment. But at this moment, the current allocation looks like this, which means P1 is allocated A already, P2 is not allocated any of the resources, P3 is allocated with D. So the first step is to create a resource allocation graph. So resource allocation graph, we know that processes are represented by circles, resources by rectangles, and then we see our allocated matrix, where we see that P1 is allocated an instance of A and P3 is allocated an instance of D. So we will create the assignment edges, one from A to P1 and the other from D to P3. So first step is done. Pretty easy, isn't it? So next step is to add claim edges for future requests. So we will see our matrix that is given, which means we have P1 over here. So P1 needs one of A, B and D, but it only has A, which means it will need B and D. So B and D, we need to create the claim edges for B and D. So P1 needs one instance of B and one instance of D. Similarly, P2, it has nothing allocated to it, which means it will need one of A, B and C. So we will have to create edges from P2 to A, B and C. Now P3, it has D allocated to it, so which means it just needs one of C. So we will just have one edge from P3 to C, which is a dotted edge, because these are claim edges. So this completes step 2. So our graph is getting a little complicated, but nevertheless it will make things easier in the next step. So step 3, which is the most complex step which we have, is to go through each process and its requests and try to convert the claim edge to assignment edge. So step 3, first step in step 3 is to find a process with future requests. Now we know that each of the processes needs something in future. P1 needs B and D, P2 needs A, B and C, P3 needs C. So we have to go through each of them, but let's pick P2 first. Just just randomly, let's pick P2 in this example first. So let's pick P2 and go through each of its requests. P2 has 3 requests: P2 to B, P2A and P2C. So we will go through each of them and try to convert each of these claim edges to assignment edges and then check for cycles. So first, P2 can be allocated B. So we will change the edge to assignment edge. Note B is currently not allocated to anyone, so we can very easily allocate B to P2. And in fact, let's allocate B to P2 and convert it to a assignment edge. So once we have added this edge, let's see if we have a cycle. If you notice carefully, there is actually a cycle. The cycle is from P1B, B to P2, P2 to A and A to P1. So this is a cycle that gets formed, and hence we cannot do this allocation, which means we cannot allocate B to P2 even though resource B is free and not used by anyone. So we have to revert back this to its claim edge, which means we make the B to P2 as dotted line again, and then we will go to the another edge, which is P2C. Now C is also free, but let's see what happens when we convert this claim edge to an assignment edge. So we converted this claim edge to an assignment edge. In fact, once we do it, there is another cycle that gets formed. This is a bigger cycle, which is P1 to D, D to D3, P3 and P3 to C, C to P2, P2 to A and A to P1. So this is a 5 cycle that gets created, and hence even this allocation is not possible. So we have to go back and revert back the P2C edge to its claim edge. In fact, if you notice, there is no more allocation possible for P2 because the edge P2A we cannot convert to assignment edge because A is already allocated to P1. So we cannot allocate A to P2, and hence we are done with process P2. And now we go back and we have to repeat this step for other processes. So notice we were not able to allocate any resource to P2, but now we will go and we will take the next process. Now next available processes are P1 and P3. P1 needs B and D and P3 needs C, and let's pick P3 just for the sake of convenience. And P3 we only have one edge, which is P3C over here, which is the claim edge. We can easily allocate C to P3 because C is free now, it's allocated to nothing else. So we will change that edge to assignment edge, so which means we have an edge from C to P3. Cool. Let's see if adding this created any cycle. It actually did not. Notice we do not have any cycles because we can go from P1 to D, from D to P3, but here we are stuck, we cannot form our cycle. So which means C can be safely allocated to P3, and then we will keep the allocation, which means we keep the assignment edge. So cool, now we are done with P3 as well. So we'll go to step 3 and then go to the next process and see if we can allocate its need. So P1 needs B and D. Next process is P1, which is the only one left. It needs B and D. So do let's go and allocate. So first notice we cannot allocate D because D is allocated to P3. So the only edge which we have is um, P1D, P1B, and B is also not allocated to anyone. So let's change this claim edge to the assignment edge. So we now have a new edge from B to P1, and let's see if there is a cycle. In fact, there is no cycle here because notice if even if we go from P2 to B to P1, we are stuck over here. So there is no cycle, and hence we can keep this allocation. So cool. So we are able to allocate B to P1. So great. So going through all the processes and their requests, we saw that we were able to allocate B to P1 and C to P3. So now we can go to step 4. So what does step 4 do? Step 4 sees if we can simulate and then make any of the process execute to its completion. So let's see. Can we do with P1? No, we cannot, because P1 needs D for its execution. So we cannot complete P1. P2 also we cannot complete because none of its required resources A, B, C are available. But P3 can complete because P3 now has D and C, and that's all it needs. So we can simulate process P3 and then we will complete it to execution. Once the process has completed executing, its resources, which means D and C, will now be free. So these resources are now available, and these can be now allocated to the other remaining process. And since these resources were free, we have to go back to step 3 again and then analyze or go through each of the requests of the remaining process to see if we can fulfill somebody's request. So let's do that. Let's go back to step 3 again. If you notice, our graph has condensed a bit because P3 has been removed now, because P3 has got completed. So coming back to step 3 again, we have to find a process with future requests. So we have P1 needs B and D, P2 needs A, B and C. So let's just pick P2 for the sake of convenience. So because P2 was not able to allocate anything earlier, so we will go through each of its requests, which means P2B, P2A and P2C, and try to convert each of those claim edges to assignment edges and see what happens. So let's first allocate P2 to B. Now if we allocate P2 to B, notice the situation hasn't changed. If we allocate P2 to B, it will be like this, and we will end up in having a cycle, which is P1B, P2B, P1B, B, P2, P2A and P1, and hence we cannot perform this allocation. So P2 still cannot be allocated B. So we will convert this claim edge, convert this assignment edge back to claim edge, and then we will go to P2's next request. So P2's next request is C, and notice C is now free because there are no other pending requests on C. In fact, we will go ahead and change the claim edge to assignment edge. So there is an edge from C to P2, and notice adding this edge did not end up in causing any cycle. So cool, at least P2 got allocated one resource, which is C. Now the other edge is P2A, but P2A edge we cannot convert to an assignment edge because A is already allocated to P1. Hence we have to leave P2 now and again repeat back step 3 with process P1. So no more allocations possible for P2. We will repeat step 3 with process P1. P1 now has already two resources, which is B and A, and there is only one allocation request, which is D. And notice D is also free, so we can easily allocate P1 to D and change the request edge P1D to assignment edge from D to P1. Adding this does not cause any cycle, and hence we will keep the allocation. So finally we are done with all the processes and their requests after the change. So we will go to step 4 again to see if we can simulate completion of the processes, any of the processes. So we go to step 4 now. So step 4 is to simulate execution of possible processes and free their resources. So what do we have? P2, we have P1, and in fact P1 has all the resources it needs, A, B and D, so that they can complete. So cool, we will then make sure P1 is completed, and once P1 is completed we'll remove P1 and its edges from B and D. But notice we still cannot complete P2 because P2 has 2 claim edges, which means P2 still needs A and B to be allocated to itself so that it can be executed. So we complete P1 and we remove P1. So finally our graph, we are only left with P2 and 3 edges. And in fact resources A and B are now released and they are readily available to P2. And now we go back to step 3 where we check back the requests of each remaining processes and see if we can allocate any resource to any process. Now if you just notice the graph, you would see that there is only one process, so there will be no issue in allocation. And in fact in step 3 we just start with P2, which needs A and B, and we can easily allocate A and B. So we will just convert the request the claim edges to the allocation edges or assignment edges. So we will have edge from B to P2 and A to P2. And notice there are no more requests and no more processes, so we can easily go to step 4. So step 4, we will simulate execution of processes. Now P2 has all its requests met, so it can easily complete to its execution, and P2 is completed, and we will remove P2 from the graph and see now our graph has only resources left, no more processes. And in fact there are no more processes, so we cannot go back and repeat step 3 again, and we will go to step 5. So in step 5 we notice that there are no processes remaining in the graph. In fact the graph is empty, and hence we are in safe state. If let's say we had some processes still left in the graph and we were unable to execute or complete it, we would have been in an unsafe state. So cool, so the output of the algorithm is we are in a safe state. And let's see the execution order of the processes. If you remember, the way we executed is we executed P3 first, then P1 and P2. So this is the execution order, and we are finally done with applying the algorithm on the example. So thanks guys for having patience. I hope the explanation was useful to you. If not, definitely you can ask questions in the comments for the video, and I'll definitely answer to them. So before we end, here is an exercise which is very similar to the one which we did in this video. So I'll just quickly go through it. We are given a system, and the system has 5 processes and 3 resources, and remember, resources are all single instance type, and the maximum need of the resources for each process is in max, which means P1 will need A and B, P2 will need A, B and C, P5 will need A and C, P3 needs 1C, and P4 needs B. And the current state of allocation is over here. P1 is allocated A, P2 is allocated C, P4 is allocated B, and P5 is allocated. There is an issue here, I think. we will not have P5 here, so which means resource A is allocated to P1, C is allocated to P2, and B is allocated to P4. And we have to do the same thing, find if the system is in a safe state, and if the system is in a safe state, find the sequence of execution leading to its completion. Alright, thanks friends for watching this video, and definitely subscribe to our channel and see other videos that are of interest to you. Bye bye, and see you again in the next video.